Part 2 of lecture number 1. Let's get started. Now here we are going to talk about program translation. We mentioned that is one of the steps in the program development process. So let's look at it closer and in more detail. Right, so let's try to understand program translation. Now, programs are developed in what we call high-level languages. These are human-readable languages. So why do we do that? Was that the case all along? Actually, no. In the very beginning, the earliest days of computers, they were programmed using machine code in a very low-level manner. That was very difficult, challenging, error-prone, right? Time-consuming, all that. But gradually, humans found out to do it is in a much easier ways, and is to use high-level languages. High-level languages are more user-friendly, more human-friendly, like Java, Python, C. These are all basically high-level languages, right? So, and that is because it's for humans, it's easy to understand and code, right? So that's a more efficient way of doing the programming. The code that we get when we produce a program in high-level languages is called source code, right? That's another term that we learn here. Now, the thing is that computers internally, its hardware doesn't understand these high-level languages. It understands what we call machine language or machine code, which is basically ones and zeros, right? Binary data, right? So the machine language or machine code has specific ways of, specific patterns, which means a particular pattern means something, another pattern means another thing, and so forth. It's not just arbitrary thing, but basically it is a machine code, right? Now, this means, what does this mean? We develop programs in high-level languages. Machines understand machine language. So there is actually a mismatch. So what does this mean? The program in high-level languages, so the source code that we get has to be translated into machine code so that we can execute the program on a computer. Right? Imagine that there are two people who want to talk to each other, or let's say a person A wants to say something to person B, and what this person A tells is in one particular language, but the person B doesn't understand that language. So we should translate, right? So just that's basically how you can basically understand it. Now, when it comes to program translation, the program translation can be done in different ways. Actually, there are two options. One is called compilation, and that is done by, you can call it a system or a translation system, which is actually a piece of software, right? A software called a compiler. Compilation by a compiler. And the second option is with a piece of software called interpreter. So that task is called interpretation. Now, so what does this mean actually? What is the difference between compilation and interpretation? So again, that if you take the human example, right? Let's say a human person A wants to give a particular message to person B, but the person's A's language is not understood by person B. And let's say there is now a translator in between. The translator comes and wants to translate the message of A to B. So the message from A is in one language, let's say high level, and it has to be translated into the language understood by person B, let's say language B. Now there are two ways in this particular scenario, let me try to explain the difference of compilation and interpretation using that human translation example. So one way this translator can translate the message from person A to B is take the first approach is take the whole message, the full message of from person A, complete the whole message. It may be a one paragraph or one page or something like that, right? Translate all that full message into the language understood by person B and then gives it to person B, right? The complete translation of the whole thing, whole message given to person B. That's basically like the compilation by a compiler. What is the second option for the human translator? The human translator can take from the person A's message, maybe the first sentence or the first statement, and translate that and tells it to person B. And after that, the translator will look at the second statement or the sentence from person A and translate that and gives to person B, like a statement by statement translation. Now that is basically similar to what how interpretation works by an interpreter, right? So we will then look at this shortly in a little bit more detail. Now, for a given language, whether a compilation happens by a compiler or interpretation happens by an interpreter depends on whether we have a compiled implementation of the language or an interpreted implementation of the language, right? So to give you an example, now in C language scenarios, of course, you can have interpreters. I think I have heard that there have been, but in most cases, there are compilers available for C language. So C is generally a compiled implementation language. So in whatever different platforms, operating system, there are compilers available for C language, which means when you have a C program, normally what happens is we compile it using the compiler to generate the machine code and you get it executed. Whereas in certain other languages, maybe you have an interpreted implementation. In such a situation, you have an interpreter that will do interpretation, right? Of course, by looking at, we realize that for any given arbitrary language, you can come up with either maybe the compiler or interpreter or both, right? That's quite possible. But the way the particular language gets used by others, it's basically based on how actually it has been implemented, right? So here's the compilers and compilation shown with some diagram, kind of this way, so that it's easy to understand. So you have a source program here. Now compiler is sitting in the middle, that is the translator. Compiler will take the source program, the whole program as a whole, and translate into executable machine code. So that is called compilation, a form of translation. Now this executable machine code can then be executed as and when we like. After we get the executable machine code, you don't need the source program to run this one. This can run by itself. And when you run it, you give its input and you get the output, and it basically runs like that. So the execution is actually using the executable machine code. Right? And so the compilation means you get the source code program, you translate into machine code. And sometimes this just the code that you get from your own source program, once it's translated into machine code, it's referred to as object code. It's not yet executable machine code. To get it to be executable into machine code, that object code will have to be connected, combined, or linked with certain other machine code available on the system. For example, in the program that we develop, there may be certain things that rely on, let's say, in order to do input-output. We may use the system's available functionality, various functions, which we call library functions and so forth, to do input-output. And when we translate using a compiler, when we get the object code, that code itself may not be able to run or be executed by itself, because we need some functionality from the libraries to get it complete. So that is the linking part. So when we link that our object code with other machine, the system provided library codes, functions, and so forth, you get the complete executable machine code, which we can save on disk as a file, right, or set of files, and reused whenever we like. At any time you want to run, you can run it, execute it. Okay, so this is basically how compilation works. You don't need to recompile the source code. We don't even have to look at source code. But if due to some reason you find out a bug, the developers have found out a bug, or they make the modification due to some reason or some improvement and change the source code, then of course the new machine code, object code, and the executable machine code will have to be generated with the change in the source code, and the new one can be used thereafter. Now, this gives actually another benefit, another interesting scenario, if you can look at it. What is needed to run and get some work done is this executable machine code. And that is machine codes. Basically, if you just look at it, if you try to look at it, it doesn't make sense. It's simply binary data, binary code, right? Of course, there are tools that can try to do reverse engineer and do something called disassembly to generate some kind of a meaning to it. But apart from that, just by looking at executable machine code, we don't get any feeling, right, or the idea what it is doing. It's understood by the machine only. Now, this gives an interesting situation where if I develop a program and I don't want to, for whatever reason, I don't want to share my source code with others, but if I am happy to share the executable, I can do that. Or if I want to just sell my software, I can just simply sell only the machine code for interested people to buy. And that way, maybe you can keep the source code a secret or protected as intellectual property, and you can have a running business out of it. Now, that indeed is what many software companies do. Like Microsoft is software, like various commercial software is like that. One good example is various software that provided by Microsoft or some big companies like that. Right? If you use a Microsoft Windows machine and various Windows or Microsoft software, various other software, you would simply download and install those software. These are the executable machine code that it gets installed. You don't have a look at the source code. You don't get a chance. Of course, Microsoft as well as others who develops commercial software, sometimes they share code with others, but it's for additional purpose or whatever reason they may share, but that is not necessary to run our software. For example, if you want to run Microsoft Word or Microsoft PowerPoint, right, you don't need the source code. Simply the executable machine code is what we need, right? So some compiled implementation examples. Here's some, I mean, there have been so many languages out there, but here are some examples: Fortran, COBOL, C, C++, Java, Pascal. These are basically examples of compiled implementations. Right, let's go to interpreters and interpretation. Now, interpreter is basically when we already explained basically how it works. So you have a source program. The interpreter will take one statement, translate it, and execute. Right? When it executes, so interpreter actually does a translation as well as an execution. When it executes, it may have to create input and produce output. Right? So translation and execution both happens. And here you can see in contrast to the compiled approach, you don't store or generate a separate machine code that is equivalent to the source program. Right? There's no translated version saved on disk. Simply, every time you want to execute, you translate. Every time, translate, execute, like that. Whereas in the case of Compiler, you translate once, and once you have the executable machine code, you don't need to translate any further, right? After that point, you can simply reuse the executable machine code whenever you want to run it. Here, every time you run, you have to translate and execute, right? Translation is necessary. So the description is here. For each source code statement, first translate it into machine code, next execute that machine code. Translation happens every time you execute, right? And the machine code of that full original source program is neither produced nor saved, right? That's very clear. And as a result, one thing is that you might feel, of course, if you are talking about a very simple program, reasonably simple program, the computers are so fast today, you might not see any difference between a compiled program being executed and an interpreted program, because interpretation also happens quite fast. But actually, if you are really doing some certain heavy amount of computation, you might see the difference that the interpreted way of execution would be slower. Why? Every time you execute, you have to translate as well. Whereas in the compiled run, there's no translation happening the time you execute. Translation has already happened, right? You have the machine code with you. Now, some example interpreted implementations, and here we list Python as one possible example, right? And here we list Java as an example under compilation, but there is some additional description on both, right? So I would encourage you to read more details about some exceptions to what I just, so this what I explained here is some kind of a simplistic explanation, generally correct for most cases. But when it comes to actual programs, modern languages, sometimes you have a strange kind of a thing. Sometimes a mix of both compilation and interpretation can happen. For example, Java and Python are actually like that. So to give you an idea about Java, now Java programs are, first you use a Java compiler to compile. So compilation happens first. But the situation is that the result of a compilation is not machine code that is understood by a particular hardware. What is produced is another code called Java bytecode. Right? It's a general representation of some Java bytecode, and that bytecode gets executed, translated into machine code, and executed by an interpreter after that. So that is called, so it's basically this execution environment which does this translation and execution is called the Java virtual machine. Right? So in the case of Java, you can see it's actually a mix of compilation and interpretation happens. Actually speaking, Python also has something like that. Like usually Python is referred to as an interpreted language, but for reasons of optimization and fast execution, and for other reasons, it has like a two-stage process where there is some form of compilation into some intermediate code and it's executed after that. But for our work, I think we can ignore those complications and simply assume that Python is actually implemented as an interpreted form, and we will refer to this as that aspect from time to time. So that okay, Python interpreter does this, does that, and so forth, right? Right. So going a little bit further, now we have discussed about translation, but there are a few more things about what we discussed about the program under program development, and that is about various errors in programs. We said we want to test the programs for correctness, and when we test, we find that certain errors are there. So, but there are certain other errors which can even prevent you from executing. We earlier mentioned those things, like if you are programming in a particular language, If you violate the language rules, which you call grammar rules or syntax rules, then you actually have another forms of errors called syntax errors and so forth. So let's list some of these common errors in programs. First type is syntax errors. As I already mentioned, when you violate the syntax rules or the grammar rules of the source language, you get syntax errors. If you have syntax errors in a program, you cannot actually execute it because the translation itself cannot happen. Simply, you cannot translate because the compiler or the interpreter tries to understand the code and it is not complying, or it doesn't basically, it's not valid code. It has rule violations. So it will not really complete the compilation or the interpretation, so you cannot execute it, right? Of course, in the case of compiled languages, what would happen is the compiler will stop at some point and say, okay, it will indicate some error message saying on this line, this somewhere, there's error, so it will have to fix it, right? In the case of, so until you do that, the translation will not succeed. So once you fix all the syntax errors, of course, you can generate a machine code using a compiler, which you can run later. In the case of interpreters, usually what happens is, let's say you have a syntax error in line number 5, but maybe up to line number 5, line number 1, 2, 3, 4 can get executed. And then when the execution or translation happens in line number 5, then there's a syntax problem where the interpreter will complain and stop. Right? So that kind of different behavior can happen. The contrast is the case of compiled environment, the execution cannot happen because you cannot produce a executable machine code because there are syntax errors. Because in order to execute, you need to have a compiled or executable form, right? But in the case of interpreted language, you might have certain number of lines executed until you get to the line with the syntax error, right? Because it goes like statement by statement or line by line, okay? So when you have syntax errors, compiler or interpreter will complain, then we need to fix by editing the source program. Of course, a program with syntax errors cannot be executed. But yeah, I made a distinction. I made a differentiation between the compiled and interpreted environment. Basically say that in the case of interpreted languages, if you have a error somewhere down in the code and the first few lines perhaps can get executed, right? But overall, of course, the complete program will not get executed. So it's actually not successful execution, right? Only up to some extent. Okay. And okay, let's suppose now this syntax errors is actually a matter of cause of frustration for many students or anybody, beginners of programming. When we start learning programming, it's quite common to make so many mistakes in so many syntax errors in our code, right? So therefore, don't worry if that is the case with you. It is natural. At the beginning, we are not familiar with the source code that much or the rules. So you will likely make many mistakes. But compilers and interpreters are usually helpful. It will give us error messages trying to show us where the error might be and we can fix it. Of course, sometimes it can be a little difficult, but overall, you can either talk to somebody also and fix those errors and you can get them corrected. Let's suppose that sometimes you may have so many errors, syntax errors to begin with in your first program. Let's say you fix them one by one. You fix them. Sometimes you fix one problem and another syntax error is basically brought in when you are editing it, right? These are all unintentional, but that can happen. So that's why I said it can be quite frustrating. But don't worry, you have to be patient, right? have some patience and continue. One by one, check your errors and correct them. Now, let's say that, okay, finally, after maybe a couple of hours, perhaps you get your program that will have zero syntax errors. So now we are so happy. Let's say you want to execute the program and you are so excited that you want your program to work and get some results. So you execute it. Will it run correctly? Well, we don't know, because just because a program does not have syntax errors does not mean it has no other errors. It can still have bugs. A syntactically correct program is not necessarily a correct program, right? It can have perhaps several bugs, several other faults or malfunctions or other errors, right? That's basically okay. The one challenge is to correct syntax errors and make it translatable. But once that is done, still it may not work as expected. So you have to, that means due to bugs. So what kind of bugs, what kind of errors can there be? Sometimes you have when you execute your program, unexpected termination. Suddenly it crashes. You may have yourself experienced sometimes when you run various programs, applications, some software on a computer, suddenly either it's gone, you don't see it, right? Sometimes you may have another uh, surprising thing. Maybe it got stuck. It doesn't respond. So it's also a form of like a unexpected termination or unexpected, basically freezing, right? You don't see something is really progressing. So that also can happen. So things like that are generally due to what we call runtime errors, right? There's something wrong with the program or something, maybe the environment that you are running it in, right? So some other factors, some input that was provided, whatever it has caused some runtime error to situation like unexpected termination. Sometimes, okay, perhaps you may not have runtime errors in the sense that you never get, let's say, unexpected termination, but still, or unexpected hanging on, like it's basically not responding, it just got stuck there without any response. So those, let's say we don't have any of those things. Still, it may not work because the output it produces may be still not correct, right? So that means program is still not doing what it is expected to do. It produces wrong output. So this can be also due to certain errors called logic errors, right? That means somewhere in your code you have mistakenly done something due to some causing these logic errors, which leads to producing wrong outputs. Right. So these errors, you can see, of course, syntax errors is the first type you'll have to encounter and you have to basically fix. After that, you will have to do quite amount of testing to make sure that your program works correctly, that it runs in various different conditions, various different situations. It doesn't have runtime errors and logic errors. You do extensive testing usually for a professional, very serious software, commercial grade ones will have to be tested extensively. And actually in a software development companies or software development teams, the testing part is also very important part of software development. In many programming, in many software development environments, there are a separate category of people. They are called testers or quality assurance engineers. Their main task is simply to test software developed by software developers or engineers enough to make sure that it will work correctly, right? When they keep running these things with different various inputs and so forth, different testing is carried out, they sometimes come across various problems, which then they would report to the developers or software developers or programmers or software engineers, which will then be fixed by them and given back to the testers to test again. And so forth, this can go a number of cycles, right? Before you actually serious software will not be released, will not be given to the users or will not be deployed for use unless you have done enough testing, right? Sometimes you probably still cannot test all possibilities. Sometimes if it's a completely new kind of software, you might, after a certain extensive amount of testing, you still, it can be considered like an early stage, right? Maybe a alpha version or beta version. You can give it to certain limited number of users for them to use maybe on a day-to-day basis. Let's say maybe you have a new web browser you developed and you give it to some users to use the new web browser for their web browsing activities, and asking them to maybe monitor it and provide the feedback and any errors they encounter and so forth. Sometimes these information may go back to the developers or engineers without the knowledge of even these testers, because the software has been constructed in such a way that maybe every time it does various things, it will done internally certain amount of error checking and so forth, and information may be sent back to the developers, and they can actually monitor things that way also, because whatever the testing that was done internally in the software development team maybe not enough, right? So actually giving it to actual users and letting them use is actually gives much more exposure and maybe enough time and chances for uncovering further errors. All right, with that, we complete the part 2 of lecture number 1.